Let me see, how can I do this? Okay. Oh, can you see my screen, Frank?
Yes, I can see very well. Thank you.
Okay, excellent. Then I think we can start. Okay, then thank you everyone for being here today. Apologies for this small delay in the presentation, but I will try to fit with the scheduled time of 40 minutes with the talk. So first of all, thank you, Frank, for inviting me, and Ernesto. This talk will be related to a paper that we just published recently in January that it's called Understanding the Electron-Doping Mechanism in Potassium-Intercalated Single-Wall Carbon Nanotubes. This is a work that mainly my PhD student developed, and she's the one who you will hear about her along the talk. But also in a very big collaboration with Professor Duncan Mowbray and with students from Yachay Tech University like Maria Rosa Preciado and Victor Torres. So let's start with this talk. So first of all, along the talk, I'm gonna try to cover the topics of electron doping categories in carbon nanotubes. Okay, I will try to introduce you to what it's a carbon nanotube and how can we change the electronic properties of this material. I will also present to you the graphite intercalation model that I have been developing and trying to improve since my PhD studies. I will also try to introduce you to the electronic and vibronic response in single wall carbon nanotubes and how can we implement the use of this intercalation model into single wall carbon nanotubes so that we can develop a new kind of electronic system here. Okay, so at the end, I will share with you our findings. I will share with you how these findings led to a new model and theory about electronic responses in single wall carbon nanotubes, and finally, some conclusions and outlook about this work. So first of all, here, most of you know these different carbon materials. They are sp2 carbon materials. Mainly, graphene is one of the ones who has been heard a lot since 2010 when the Nobel Prize was given to Andrew Geim and Konstantin Novoselov. And during that time, graphene became extremely important for the scientific community. Everyone wanted to develop things with graphene. Everyone wants to use graphene for every single possible application because the electronic properties and the thing that graphene is a zero gap semiconductor uh, raises a lot of chances of using this material for different applications. But this is not the only one that it's important. There exists another variety of materials that are so somehow related to this graphene structure that are carbon nanotubes. Fullerens, who were also won as a Nobel Prize in 1996, and graphite, that is as I perceive it, the father of all these other structures because it's the mineral and the only one who you can find directly in nature without having to synthesize the material per se. But what is important about these materials, these different allotropes of carbon, is their electronic properties. So what mainly myself, the groups where I have been working, the group where I did my PhD, and many people around the world, is in studying and changing and modulating the electronic properties of these materials. How? How can we modulate that? Well, first of all, we need to understand that graphene, for example, is a zero gap semiconductor, okay, that we have located here arbitrarily the Fermi energy level at this point here. And then from here, we can see that we have a zero gap semiconductor in graphene. We have also carbon nanotubes, which could act as a metallic material, as a semiconductor material, or as a semi-metal. We could have these three categories here in carbon nanotubes. Graphite, it's a material that it's a p-type material. We could use it as a p-type material, as an intrinsic graphite, or as an n-type material as well. Graphite per se is a semi-metal, and we could also have fullerenes and carbon nanotubes who are act as a semiconductor, as you can see here as well, where we can have a band gap in between the valence and the conduction band. Graphene is very important. I cannot say otherwise. I also do a lot of research on graphene. It's an extremely important material, but it is also not the only one that is important here, because we also have carbon nanotubes, and carbon nanotubes are as important, interesting, and versatile materials nowadays. Carbon nanotubes, they are easier to synthesize in bulk quantities, and therefore that's one of the main possibilities that gives the interesting chance of using carbon nanotubes in real world applications, whereas graphene still lacks of bulk production or bulk synthesis of material, in this case, to be integrated to industry. So how can we change these electronic properties of all these different materials? Well, the answer is by doping. We could have substitutional doping by adding nitrogen atoms. We could add nitrogen atoms in the lattice of these carbon allotropes in a substitutional way, as you can see here. We can add them in a pyridinic way. We can add them as a pyrolytic way here. And then we can start changing the structure of the material per se. But in this case, this is not, I mean, I have been doing that, but this is not the main interest for us, because now we also have an intercalation methodology that has been working quite well in the recent years, and it can be integrated to all these different allotropes of carbon. It can be used in graphite, it can be used in graphene, and in 2016, we proved that also multi-wall carbon nanotubes, and in this case, can also be doped in a way that we can turn the optical properties of the material, turning multi-wall carbon nanotubes from black into golden carbon nanotubes. This is something extremely, extremely interesting, because all these optical changes, they are derived from the integration of potassium within the potassium or alkali metals, metals that donate electrons into the carbon structure, so that the material gets an excess of electrons, and that moves the Fermi energy level into a place where we can access different bands from the electronic band structure of the material, and that per se changes the electronic properties of the material, the optical properties of the material, the mechanical properties of the material. But as I said, I'm interested now in discussing with you the electronic properties of these carbon nanostructures. So, once again, graphite intercalation compounds will be the solution that I will present today during this presentation. How can we dope carbon nanotubes with electron donors? There exist several ways. In this case, you can observe here that there exists a model that it's called the endohedral doping, by filling carbon nanotubes with electron donor molecules or atoms. We can also have an exohedral doping, where the alkali metal or the metal in general that it's donating and giving electrons to the carbon nanotubes stays around the carbon nanotubes, creating a superstructure that altogether behaves as a single big large compound. Okay, this is actually one of the most interesting. And also we have the possibility of having an in-play doping, where the atoms who donate electrons stays in between the layers of the carbon allotrope material, in this case in between the layers of the nanotubes. The first people who tried to do this kind of in-plane doping or interlayer doping, they found an interesting result because they wanted to dope the material, but then at the time that they were doping, the atoms started to enter the planes of the carbon nanotube, and then they started to break the carbon nanotube, and they created what it's called now multiple carbon nanoribbons or nanoribbons of graphene, okay, by integrating these alkali metals in between the layers that break the structure of the carbon nanotube and create these long layers of carbon material, okay? So then, coming from here, coming from this point, we can get back to 1981, where Professor Dresselhaus, who passed away a couple of years ago, yeah, she was the very first person who was really interested in discovering and describing all these different electronic properties when we intercalate alkali metals, metals like lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium, into the layers of graphene, particularly in graphite. Okay, this one is a graphite, a graphitic structure. And when we place these alkali metals in between the layers, we create what I just mentioned, a big compound, like the one that we see in figure B. It's a big compound. The whole system behaves as a single unit. And in 2007, it was discovered that when we put calcium in between these layers, we create a compound like calcium C6, 6 atoms of carbon per calcium atom. And when we create that system, we have a superconducting system that has a 10 Kelvin transition superconducting temperature. Okay. In this case, people got again super interested about using alkali metals in order to create superconducting materials. But the main properties of these materials were still not absolutely known. And that's why Professor Dresselhaus in 1881, she was studying all these different properties and describing how is it possible that we can create this system and how is it possible that the alkali metals order and have a preferential order in between the graphitic layers. She developed this technique that is extremely easy in one sense. It's actually the technique that I have been using since I started my PhD. And in this technique, we only have an ampoule, a quartz ampoule like the one that you see here, this quartz ampoule that we see here. On one side of the ampoule, this ampoule, we seal it in vacuum, and on one side we have the pristine material. It could be CNTs, it could be graphite, it could be graphene, it could be any of these carbon nanostructures that we already mentioned. We narrow one side from the other, and on the other side we have the alkali material. It could be potassium, it could be cesium, it could be rubidium, it could be any of these alkali metals. Then, basically what we do is to evaporate the molecules so that the atoms start to intercalate in between the layers of the graphitic material. Important, all of this has to be done in vacuum, because otherwise, if we don't do it in vacuum, then what will happen is that the alkali metal that we have here, it will react with water from the environment, and then you will never be able to do this. You will be never able to create an intercalation compound. You need an extremely pure system, and you also need to have a gradient of temperature between the intercalant and the host material that you will use. This is actually what we have here on figure B, where we see that the difference in temperature will give us certain stages of intercalation. Stage 1 is where we reach the highest concentration of alkali metal per carbon atom. And in this point, at this point is where we get this kind of superconductivity behavior in alkali dope materials. So this is just basically like an introduction for you to understand what, how did we made the experiment for this paper, so that you understand how do we follow up with with the experimental part on the paper. Then we come back to carbon nanotubes, and in carbon nanotubes, as we can see here, we have this Dirac cone that is actually cut in sections. These sections that we see here are different energetic levels that are derived from the one-dimensionality of carbon nanotubes. The carbon nanotubes are a one-dimensional system, okay? They only grow on this 1D, and due to this figure that they have, then we have this particular kind of density of states where we have very specific energetic levels between the valence and the conduction band. We could have a semiconductor system, a semiconductor carbon nanotube, where we have a band gap. And then, as you can see here, we could have transitions between each energetic level. These ones we call S11, S22, S23, etc. And those S11 or those transitions are nothing but a transition between the valence and the conduction band that we have in semiconductor material, in a semiconductor carbon nanotube. In a metallic carbon nanotube, we do not have that kind of situation, because we do have we don't have a band gap, but still we have a transition between the valence and the conduction band. Each of these transitions, they are called in the term of carbon nanotubes terminology as a Van Hoff singularity. It's very interesting because now what we have discovered is that there is a relation between these Van Hoff singularities and what we just found when we doped the carbon nanotubes with an alkali metal donor. So this is what we are going to see today. How do we evince, or how do we understand which kind of carbon nanotubes do we have? So basically, when you take a carbon nanotube, you will see a black material. But if you analyze, if you use a Raman spectrometer to perform the analysis of single wall carbon nanotubes, you will see that in the region between 100 to 300 centimeters to the -1, you will find these very intense and characteristic peaks. Each of those peaks, they are related, directly related to the kind of nanotube that we have on the sample. Basically, each peak tells you if it's a metallic or a semiconductor carbon nanotube. If it's a metallic, it will be located in this region. If it's a semiconducting carbon nanotube, it will be located in this region. You see that in a HIPCO sample semiconducting, that it's enriched semiconducting, that it has majority of the material as semiconductor, then you see that that these peaks only appear here in this region, but still we do have a tiny, tiny, tiny amount of them here, okay? But a little amount, but enough to know that we do not have a completely pure sample, okay? It is possible to get pure sample, absolutely pure, but in this case, for our experiment, it was much better to have them slightly combined, because in this case, then we can use it to get a complete picture of how does this carbon nanotubes behave under different conditions. So what we did here is to take metallic HIPCO carbon nanotubes and semiconducting HIPCO carbon nanotubes in order to expose them to potassium, as we just show here, exactly as we did here. We expose them to potassium, that is an alkali metal that donates electrons, that gives electrons to the carbon nanotube, and then we analyze the region of the RBMs, and the RBMs, I forgot to mention, it's a vibration that you observe here, where the atom looks like if it's like it is breathing. In this case, it's like opening and closing somehow. There is a stretch in the bones outwards and inwards, so that it looks like it were breathing like our lungs. This is a very well-known process. It's a process that is not new. It's something that it has been studied for a long time, and there is a very nice paper of Thompson, Reich, and Malch in 2005 in PRB, where they describe these kind of processes in single-wall carbon nanotubes. But what is interesting here is that we found a way to correlate these particular modes to the interaction of semiconducting and metallic carbon nanotubes to the presence of excess of electrons in the structure. How do you identify if in your sample you have a metallic or how do you identify if it's a metallic or a semiconducting carbon nanotube? Extremely simple. You can basically take the position of this peak. This position in centimeters to the -1 is related to a specific diameter here. And this diameter here is related to this breathing mode, to the radial breathing mode. So then you can go to this periodic table of carbon nanotubes, and in the periodic table, you can look for the specific diameter that you just found, and that will tell you which kind of nanotube do you have. Basically, by using this simple equation with some constants that are explained in this paper, okay? And then by measuring the frequency, by looking at the frequency that you found in your Raman spectra of the RBM, then you can extract the diameter, and then you can tell me if it's a metallic or if it's a semiconducting carbon nanotube. That is actually very simple. This has been done. There are a lot of tables where they tell you a very big list of carbon nanotubes according to this frequency that it has been found here and related to this diameter and so on. But this is we went a little bit beyond that. Because what we wanted to see is how does this equation relates to the presence of electrons, excess of electrons. If I add electrons to this system, how does the diameter gets affected? Ideally should not get affected. I mean, why should it be? But you will see that there is an affection directly to the diameter, and you will see that there is an extremely large effect coming into the radial breathing mode that is related to this diameter that we just mentioned here, okay? So again, this is just the introduction. Now let's come to the results. That is what the reason of this webinar was about. So in this case, what we did is to take single wall carbon nanotubes, HIPCO single wall carbon nanotubes, semiconducting and metallic. We expose them to potassium. Potassium is an electron donor. And we create this gradient of temperature in order to evaporate the potassium molecules onto the surface of the carbon nanotube, and everything was done under ultra high vacuum conditions, okay, approximately 10 to the -8 millibars. This was already done once by Kukobesh, Pichler, Kamberger, and Kosmani group in Vienna. They found some interesting things about this effect. They found that when you expose this alkali metal on the surface of these carbon nanotubes, if you have a combination of semiconducting and metallic system, if your sample is a combined sample, then after this process, everything becomes metallic. That was the main result they found. Everything becomes metallic, and at some point it makes sense. It makes sense because if you are giving electrons to a semiconducting system, then it should turn metallic somehow because you are moving or displacing the Fermi energy level. So in this case, you have a fully metallic sample. But that system was not analyzed. It was analyzed, but not deep in detail, so that we could extract a detailed description of this mechanism of how does that happen. Because ideally, electrons should go to the most favorable system. Which of these two? Well, this is what we are going to see now. So here you can see that we were monitoring the charging process. We were giving the electrons to the single wall carbon nanotubes. in situ during these high vacuum conditions, and every few seconds at the beginning, we were measuring the changes in the RBM modes as a function of exposure to potassium. You can see here our, we have four different samples. We have this hypcometallic, hypco-semiconducting. You see the development of the Raman peaks, but what you see here, if you take a close look to this region here, we see that the RBMs who are distinctive for each kind of carbon nanotube, for metallic or semiconducting, they start to disappear. When they start to disappear, then at this particular point, we got intrigued because we said, okay, what's the reason why they disappear? Why do they go away? I mean, we are not destroying the carbon nanotubes. We know that for sure. And we know that we are giving electrons, but why do they go away? Are they out of resonance? Are they so doped that now the Raman cannot see them? Are the electronic property or the optical properties changed? So what we see here step by step is that some of these peaks started to go away first than others. We identify which kind of nanotubes we had, but we needed to tell the community what was really happening with the carbon nanotubes. Why did they go away on the measurement, during the measurement? Why did the RBM disappear? It's not that we are destroying the carbon nanotubes, but something is happening there. What is happening is the following. First of all, this is our pristine material, the material at the very beginning before we did any intercalation. So we had the hypcometallic and hypco-semiconducting sample. We identify which kind of nanotubes did we had. Okay, we had these different chiralities. Each of those chiralities corresponds to a specific diameter. Okay, and the only way to confirm that the Raman analysis that we did, that it was correct, it was by performing a parallel photoluminescence analysis. That is this one that you can see on the left side. The photoluminescence analysis, it tells us the precise carbon nanotube that we have present on the sample, because each of these different diameters and different chiralities, they have a very particular excitation energy, excitation wavelength, where they are in resonance, where the RBM mode starts to breathe much faster or larger. So we have this RBM. I will try to make a nice draw here, okay, where they go out or inwards, okay, and this vibration starts to get much enhanced when we are at the specific excitation wavelength for each carbon nanotube. So in this case, the measurements that we were performing here, they were done at 633 nanometers. So if at this wavelength, we expect to have more in resonance something here. So we are closer to the 8.4. So the 8.4 should be one of the nanotubes that we see, that we should see the most if it were present in the sample. And also the 7.6 was not too far. So all the nanotubes that were close to the 633 region, they should be present here in this analysis. And this is actually why we were analyzing the 8.4 like one of the most important ones on this analysis. Okay. Then we did after we knew for sure which kind of nanotubes did we had in the sample. Then we did the intercalation. We took potassium, put it into a sealed capsule. We put the single wall carbon nanotubes, we evaporate the potassium, and then we ended up with this kind of system that we had here. We see that during the evolution, the RBM, after 3 minutes, 9, 16, 17, 18, 28 final, then we see that the RBMs start to disappear as we observed at the very beginning. This one was the controlled step-by-step experiment that we performed. We see that at the very final step, we have no presence, apparently no presence of the single wall carbon nanotubes, because now they are gone here from the RBM region. And that happened in the semiconducting sample and in the metallic sample. In both samples, we had exactly the same situation. But we see that here, this peak that it's located here in the semiconducting, it took longer to disappear than the peaks on the left side that are the metallic ones, you see? So the metallics, now we have a hint about how the behavior of this material goes. We see that the metallic peaks here goes first out, than the semiconducting ones. So we started to dig into this information to find out why is this situation occurring? Why are we losing first one of this kind of material of metallic nanotubes first, and then the other one? So after we did that, we only focus on this section. We did not study the very final material. We present the final one here, but we did not study that one because there we have no RBMs any longer. But before that, we had all the peaks still here, and that's what we analyzed. So we did assume, so we took this region from this region here, the red one, and this region here. And we took those two regions and we made a very detailed analysis from all the different carbon nanotubes that we had present in the sample. So from the pristine material that has no doping, we took each of the peaks and then we see how they were changing and which of them was disappearing first. The first thing that we observe, and it's very clear from here, is that we have a shift. The position, the final position of these peaks is not exactly the same as the very beginning. Okay, so this is difficult to do. I'm doing my best. So if you see here, we have a shift from the original position of the RBM peaks into the very final step. That was our first indication. When we see the semiconducting sample, we see that these 10-3 peak, or these peaks that we have here on the left, they tend to go absolutely away. And also the peaks that we have here on the right, they also tend to go away, okay? But we also have kind of a shifting from the initial to the final step. So we had to analyze now several things. We had to analyze the position, the frequency, the initial frequency of the material with respect to the final analysis. And we also need to analyze what is happening to the metallic nanotubes according to this characteristics, which are metallics and which ones are semiconducting. And we need to see which one gets more affected and why, in order to give a full description of the mechanism of doping here. For that, we need the help of theory. So we got some calculations down here. So in theory, when we take the material from a zero doping, zero charge here, from a zero charge down to minus 18 milli-electron volts per carbon atom, that it's extremely huge amount of electrons on the system, okay? That is an extremely high. We never get there. We are here in the red arrow here. So this is where we are. So when we are here, we see that there is kind of a step-like function that it's more evident when we analyze a 10-0 carbon nanotube. When we analyze an 8-4 or a 10-0 carbon nanotube, we see that there is kind of a step-like function that tells us that as we are increasing the concentration of electrons in the sample, then we also have a change in the frequency of this radial breathing mode in the Raman spectra, which is actually what we just observed here. So we have a change in frequency as a function of so the less doping, it's moved to lower frequencies, and this is actually what we just found here. So we have a reduction in the frequency as a function of increasing the electron concentration in the sample. But there are some places where we have kind of a plateau region that it's also interesting to know why do we have this kind of plateau regions here. It's not kind of a constant reduction of frequency as a function of doping, but it's something that gets step by step. When we have this analysis, when we see this kind of behavior, then we analyzed our experimental results, and then we see that when we increase the concentration of electrons in the sample, this region here, when we increase that concentration of electrons, we also get a reduction on this RBM frequency. And then at one point, we have kind of a drop here. The drop tells us that we were reaching this point here. Let me change the color. So we are reaching this point here where we drop our frequency, and we are reaching one of these step-like moments in concentration of electrons along the presence of the carbon nanotubes. Then we are reaching those ones here, and then we observe that we have a constant reduction of frequency, then blop, it drops down because we reach one of these step-like moments at the presence of the material. But then what's the meaning of that? Why do we have this kind of situation? Where the reason why do we have this kind of situation is because according to this graph that we observe here, we can see that we are increasing, as we increase the amount of electrons, we also displace or shift the Fermi energy level, okay, with respect to the conduction band minimum. That means that we are crossing the Fermi energy level. We are crossing these Van Hoff singularities, and then we are filling the valence band from the conduction band with an excess of electrons on the system. And that's the reason why we get steps. The steps are related to each of the Van Hoff singularities crossings that we could get in the different samples, depending if it's semiconducting or a metallic material. So we proved that with this experimental result, because we got the kind of drop-down step, like we got it for the semiconducting sample. This is the semiconducting, and we got it also for the metallic sample, where we have this kind of behavior but going in the opposite direction of the shift. In this case, they behave opposite one to the other. So we can, at this point, we started to make conclusions. Our first conclusion was that in the RBM shift, our first conclusion is this one here. In the RBM shift, in the change in the frequency that we had, we got an electron doping that is proportional to the single wall carbon nanotubes density of states, because we are crossing the Fermi, we are crossing each Van Hoff singularity when we reach certain amount of electron concentration. And that, of course, is related to the diameter, because each different carbon nanotube has a different density of states. So that makes absolutely sense. Now it sounds very easy, but it took us quite long to understand that. But at this point, we got it. Then we can say that away from the Van Hoff singularities, the single wall carbon nanotubes density of states is relatively constant. Okay, so when we are in the step-like function, we got kind of a constant reduction of frequency as we increase the concentration of electrons, but we are not yet feeling the second or the third Van Hoff singularity, which is actually what we managed to do when we increase the electron concentration. Then we are getting close to the last part of the talk, because now we are understanding everything what is happening, and we are able to create a description of the mechanism of doping in single wall carbon nanotubes. We have our semiconducting carbon nanotubes, and we have our metallic carbon nanotubes. In the semiconducting carbon nanotubes, we cross a Van Hoff singularity when we have enough electrons to be shared between the alkali metal doping and the carbon nanotube. And then this excess of electrons help us to cross the first Van Hoff singularity, the S11. Then we increase the electron concentration, and then boom, we have a second jump into the second Van Hoff singularity, and so on, if we could continue. And in the case of the metallic ones, that also occurs, but in this case, we need to cross larger regions or different regions of Van Hoff singularities. But in this case, what we can tell also at this point is that our semiconducting materials are extracting a lot of these electrons, and the metallic ones are, as they are already metallic, they don't require a lot of these electrons. They just require a portion of them. So we could get a picture, a very nice picture from the experimental electron concentration, the experimental energy from this transition, and this and that will compare to the theoretical energy level, energetic level, that each of them is related to different carbon nanotubes, that they have different diameters, that they have different chiralities, and then all of them fall into this line because now our experimental result tell us that we cross the Fermi energy level of each of them at exactly the same theoretical or expected energy transition from each Van Hoff singularity. Then we were able to create kind of a new or novel design of this kind of this periodic table of carbon nanotubes. So we just give more information. So people already published the periodic table of carbon nanotubes, but now we were able to give a picture of a new periodic table where you see that as a function of metallicity of the carbon nanotube, there exists a correlation. If we take the nanotubes from the top bottom, we will see that the RBM Raman shift of the RBM that you will observe in Raman will shift downwards, so you will have lower wave numbers if you take if you displace from carbon nanotubes that are located in the top part of this periodic table with respect to the ones that we have at the bottom. Okay, so we take this periodic table that already exists, and then from there we see that there is a correlation of downshift. So we will have always lower frequency values for carbon nanotubes that are located at the bottom here with respect to the ones that are at the top. We also found a correlation related to the diameter dependence. So in this case, when the diameter, when we increase the metallicity of these carbon nanotubes, we will see that there is a chiral dependence on this diameter in this direction, and there is a dependence on this direction with respect to the band gap and density of states. So we are able now to get a different the behavior to tell who will be doped first. This nanotube will be doped first, and then this one will be doped, and then this one will be doped first, and this one will be doped afterwards. So we are able to tell now to the community which carbon nanotube in their samples will be affected first by adding electrons, and then now you won't be guessing about what is happening into the sample. You are able to tell in a correct way which nanotube gets affected first and which one later on. Okay. Finally, in my conclusions here, I can tell you 4 main things that we discover with this work. First of all, metallic single wall carbon nanotubes are doped first because they don't need too much excess of electrons in order to cross each Van Hoff singularity. They require a very minimum amount of electrons because they are already metallic. Okay, So then in this case, they get immediately shifted. You will see immediately the RBM to be shifted. Then the final RBM frequency shift in metallic single-wall carbon nanotubes can be assumed to be a combinational effect from a carbon-carbon bonding weakening and the electron phonon coupling effect. Why do I say this? Because at the time that you increase the amount of electrons, and as all this system behaves as a single unit, then the radial breathing mode will be affected because you have atoms, potassium atoms around the nanotube. You will have your nanotube, and then you will have potassium atoms around who are not helping in the movement of the whole system when it's breathing. So in this case, that movement gets affected. Thus, we have a weakening on this carbon-carbon bond, also because the pi bond that is delocalized from this sp2 structure, it's attached to the potassium that it's around the tube per se. The third thing that we found is that in semiconducting single-wall carbon nanotubes, the RBM downshift is directly proportional to the diameter. So the larger the diameter, it will take longer to be affected on the Raman spectra. And that also makes sense because if we have a tiny nanotube compared to a very big nanotube, this one will get easy enough potassium atoms around so that it gets extremely affected in comparison to a very large carbon nanotube that requires of potassium atoms around. Then finally, and that is absolutely related to the density of states of each of them, that is related to the diameter. Finally, when we're having both systems, metallic and semiconducting carbon nanotubes, then the electron doping will directly depend on both things, the diameter and the electric density of states, because we need to fulfill the each Van Hoff singularity, and that directly depends on the diameter of the tube that is present on the sample. So with this, I want to finish my talk today. I need to first acknowledge all the people who were working with me in this project. Especially, I want to thank Claudia Krockel from FAO University. She is actually the one who was doing all this amazing work related to the doping of carbon nanotubes, and she's actually the one who found this interesting behavior in the RBMs. From there is that we were starting to develop this project and found these interesting results. Also, I want to thank our students, Maria Rosa, Victor Torres, who were directed by Professor Duncan Mowbray, and in this case, they were the ones who mainly make the description of the mechanism that in theory confirmed our experimental results. Professor Stephanie Reich, Professor Andreas Hirsch, and Professor Frank Hauke from Germany, the three of them were helping in the understanding of this full mechanism and getting the full paper to get completed at the very end. So with this, I want also to thank the financial representative for this project, the DRS from Freie Universität, the synthetic carbon allotropes from the DFG as project 1 from the Nuremberg ZMP department at FAO University, who are the ones who were paying for all the things that we needed for this project and all the different syntheses that we required. And of course, Yachay Tech and with the university, who are now my two affiliations. So with this, I want to thank you, and I appreciate the time that you stay here, and I will be open for all your questions.
Well, I really want to thank you, Julio, for this excellent. The way we're going to do with the question is, you know, this webinar, I really like it, but managing the question can be a little bit difficult. So the way I would like to suggest is that everybody who has a question can write the question. Okay, so we have an order. We know which question is. And then Julio, if you can help to answer one by one. And if there are any comments by the professors or the students who ask questions, I suggest that they can on the microphone and do a comment one by one. Okay, this is my suggestion, and so I would like to open some time for questions, and then I will need Julio to address them.
Okay, perfect.
Please write your question and put it on the chat so that Julio and everybody can see it, and Julio can respond to it.
Okay, so the first question comes from Carlos Reynoso, and it says, thank you, Carlos, for your congratulations, and it says that he would like to know what is happening with the 2D peak. Yeah, I didn't have time, and actually we didn't discuss that in the paper. We were more focused into the part that is related to the RBN mode. But if I get quickly to this picture here, to this one here, we see that the 2D line, that is this peak that you see here on higher wave numbers, okay, the 2D line disappears as a function of doping. This is actually a behavior that it's really well known. The 2D line disappears because now after a lot of electrons are present on the sample, then you displace the Fermi energy level high enough so that the double resonance process doesn't exist any longer. Of course, there should be a correlation because each of these double resonance process must contain all the different 2D lines for each carbon nanotube, but it's really hard to describe because we have a very broad peak here and we need to make a deconvolution of several components that should be correlated to each of the nanotubes that we have here, and that will be a really complicated analysis. It's possible, yes, I won't say no, and we are actually now working on that part, but the only thing that I can tell you is as a function of doping, the 2D line should disappear, and this is actually what we observe here. At one point, we have no 2D line any longer. That is actually what it was expected. Okay, so there is another question here. Thank you, Manuel. Why did I select potassium for doping? And if I can generalize this analysis for another carbon materials. Yes, actually, I select potassium because I have been working with potassium since my PhD, so already 10 years. And it's a very nice guy to create the doping. So it's very easy to evaporate potassium and to see and analyze it. But actually, this can be done for also with rubidium. It can also be done with cesium, lithium, and many other materials, many other alkali metals. Yes, it can be generalized in that sense. But I use it for convenience because it's the one that we have more understood yet at the moment. And also because if you would like to use calcium, for example, or if you would like to use lithium, you cannot evaporate as this. You need to have a different system in order to create the doping, but it's possible. You can reach higher electron concentrations with calcium. It can be generalized. Yes, it is possible to be generalized, but of course we are now working in performing these experiments with another metals. Now we are doing it with calcium, and we have been done that with lithium as well. So thank you, Manuel. Now from Antonio Diaz, Thank you, Antonio. So it says, yes, of course. So he's asking, Antonio is asking about the use of biosensors, that this kind of material may be used for biosensing applications. Yes, the answer is absolutely yes. So actually the idea of doping now, and this is actually the paper that we are working afterwards, that now at the moment we are working with my PhD student, is to functionalize this system. So once it's doped, then we have a shift on the Fermi energy level. Then we are able to create a system that it's extremely, that it has a very, very high chemical chemical reactivity, and this chemical reactivity leads to the possibility to be functionalized. So we could attach different molecules or different, yeah, different molecules like hydrogen, hydroxides, and large molecules also to these nanotubes, and then they can be definitely used as a sensor. We are now doing that for graphene. We are already actually now writing the paper, but I can tell you that graphene gets functionalized, and we are able to control which kind of molecule gets attached to the surface of the graphene. And the idea is that that can be used now as a sensor material. So we are now working on this. So it's absolutely possible, Antonio. Thank you very much for your question. Marvin, thank you very much for the congratulations. Then now from Avila, it says, thank you for the presentation. Thank you very much. The question is related about the peaks in the region from 500, 150 and 300. Do they specifically indicate the level of potassium intercalation? Is there another technique that corroborates it? Yes. Sorry. They do not tell us precisely how much of potassium do we have on the sample. For that, you need another technique, either a mass spectrometer or an XPS spectrometer. But we are able to, so if I am able to get back here a little bit, so when you see here this analysis, we are able to roughly calculate the concentration of potassium in along the reaction. So we got a rough estimation that it's quite good. Okay, it's not a mass spectrometer. It is not an XPS analysis where we can really tell the concentration. But the only thing that I can tell you also is that we know that when you get the highest concentration, we are in the KC8 phase. So we know that below that, um, until we don't get, if we still see the 2D line, then here we are something in KC36 or something. Then when we don't see the 2D line any longer, that was one of the very first questions, then we are in the KC24. And this is something that in the literature we have been presenting for the past few years. So we know roughly how much does the concentration of potassium per carbon atom it's on the sample by reading the 2D line and the shift of the G line as a function of doping. So we don't know precisely. Another technique that can be used will be a mass spectrometer, or it could be, in this case, the use of XPS spectroscopy. So that will be the only way to resolve that. Joshua, thank you, Joshua, very much for the congratulations. And he says, why does the low wave number signals disappear after 19 minutes of measurements? And the reason why they disappear is because they get out of resonance. At the time that you move the Fermi energy level, now you are working with a material that is not resonant any longer at the wave of the excitation energy. So if you see here, the original excitation energy of the 8.4, it's something below 600, But then afterwards, when we increase when we displace the Fermi energy level because we dope the material, then we are out of resonance because we move into a higher wave numbers. That's the reason why we don't see these nanotubes any longer. Then from Maria Paula, thank you, Maria Paula, for your comments here. And she says, could this process be done with an acceptor or only with donors? No, it can also be done with acceptors. Absolutely. So actually, this work, I can remember, but in Berlin, they are actually now at the moment they have done something similar, not with nanotubes, but with graphene, and they are using iron trichloride as a donor, as an electron acceptor. So it can be done the other way around, and then we can extract and see the behavior of this material the other way around. But in this case, iron trichloride, for example, is a little bit more messy, and I am not working at the moment with that one, but I have done a couple experiments with it, and I know that it works quite well. But I mean, an additional study should be required to do it with an acceptor. So it can be done with both. That's for sure. Then Antonio, he is asking about the work of Andrei Koblistov, in which he uses chemical reactions inside the CNT to monitor the atomic level of TM. Yes, well, in this case, Andre, they are working actually in doing these chemical reactions, but mainly with iron inside the nanotubes. This is something absolutely different than this work, in the sense that the chemical reaction that occurs inside of a nanotube uh, provokes the possibility that you break the symmetry inside of the tube. If you have a double wall, you can convert the double wall into a single wall, for example. Or if you have a multi-wall, you can create a double wall, or you can create different kind of structures, or you can get the linear change, for example, that Paola Ayala published. That is absolutely possible, and it's only possible because you have an electron acceptor inside the nanotube. So at the time that the chemical reaction occurs, then it starts to attract the carbon atoms and creates an internal reaction that is not only related to this chemistry, but it's also related to pressure and mechanical stress inside the tube. And that's the reason why the system gets broken. And at that point, you can create different nanostructures inside the nanotube. That one is a totally different field, but I know that it's also somehow related because you need electron acceptors inside the nanotube so that it works. So Frank is asking, do I can have more sensitivity or more specific sensors? Well, actually, this is what I am aiming for. So this is actually my goal for once I publish a couple of papers this year. Our goal next year is actually to start testing these graphene and carbon nanotube sensors. Our plan is to, now we have the material already doped. Now we are exposing it to different molecules in order to create a functionalized system. And then when the material gets functionalized, ideally it should be extremely sharp because now we have a very specific Fermi energy level and electronegativity of the material. So ideally should be more sensitive or more specific in this case. But this is something that we are testing, and I cannot say yes or no yet, but I hope yes. Let me see. Thank you everyone for the comments here. So the final two questions: have I measured the electrical properties of these intercalated nanotubes? No, not directly. In order to do that, I would have to do the measurements in situ inside of this high vacuum vessel. And unfortunately, I haven't created that setup yet. The setup is ready in Vienna, but I haven't done those experiments yet because first we wanted to understand the mechanism. Now we know. So now in case that we want to create a Now, in case that we want to create this kind of a special superconducting system or superconducting structure, then we will need to have a system inside the vacuum that could measure under low temperature so that we can trace the changes in the conductivity of the material, for instance. Then we will trace more the electronic properties of the carbon atoms. We know that they are changed, of course, because we already displaced the Fermi energy level. We have a metallic system, but I haven't measured it per se. But yes, thank you very much to everyone for your questions. And any other questions, for sure you know where to find me. And you can send me any email so that we can work a little bit longer.
Yeah, I would like to thank you again, Julio, okay? I would like to thank everybody who connected for this presentation. We will do this about twice a week. We have some outstanding speakers from Yachay Tech, from Ecuador, and from the world that will join us. And again, I hope we can learn, continue to be connected with our research, although that we cannot go to the lab. We can still continue to share our experience and our results. So thank you again, Julio, and I hope we see you soon. Thank you everyone again, and please connect to the future webinars if you can, if you're available.
Thank you very much, Frank, and thank you to everyone. Have a great night.